Hello everyone, welcome to the last lecture of week 3 of the course Simulation of Modern Power Systems. In this discussion, we will start with our next important module on contingency analysis or security analysis, and in this opening discussion on module of contingency analysis, we will first understand what actually is power system security, for which this contingency or otherwise also known as security analysis needs to be learned, needs to be understood, and what are the typical process flow based models that are used to understand whether power system is operating in a secured fashion or in a insecured fashion. So, to give you an idea of what we are going to learn in this discussion, we will first of all understand what is a contingency, then what has this contingency to do with security, and to be specific, what is specifically this power system security, based on which the corresponding models help us understand that what is the corresponding state of the power network or power system in terms of corresponding security. The last few discussions, we opened up our discussion with basic introduction to power systems, how the network has evolved over the years, decades, centuries, and the usual Kirchhoff's law based analysis, circuit analysis. What is it? The idea behind basic circuit analysis was, if our sources are defined in terms of voltage or current source directly, then by circuit analysis for a given electric circuit, we will be able to find other voltage and currents as and when required. The same circuit analysis, if it is to be done for power system where sources are defined as voltage or current source, the same would have been true, but the problem with the sources in conventional or conventional sources in power systems is that the sources are defined in terms of power, which is inherently product of voltage and current, as a result of which the same circuit analysis principles, if they were applied on power, they would become nonlinear equations, and as a result of which the module on power flow analysis was discussed, which explained several techniques of solving power flow equations, which are analogous circuit based equations for a given electric circuit. And we also understood different techniques. Techniques varied from Gauss-Seidel method to Newton-Raphson method. Then we had fast decoupled power flow and eventually DC power flow for high voltage transmission networks. The reason I am not writing GSPF or NRPF is because Gauss-Seidel and Newton-Raphson are generic techniques which can be used to solve other nonlinear linear mathematical equations, whereas fast decoupled power flow and DC power flow are specific to only power flow equations or power flow analysis. The other aspect of discussing these topics was that these two tools, specifically DC power flow, is going to be extensively used in contingency or security analysis, which is our current module that we will take up. So, any viewer who hasn't understood DC power flow, I would request to please refer to the corresponding lecture where the DC power flow has been explained at length along with a numeric example, so that application to contingency and security analysis will become clear. So, in order to understand what contingency analysis is, I will start with certain events which have happened in power networks across the globe, not only in India but across the globe, which has led to loss of security or loss of generation load balancing in conventional power network. So, one of those events which is detrimental, disastrous to the operation of power networks is the event of blackouts. As the term blackout says, the network which was supposed to be energized, which was supposed to transmit power from generation stations to load ends, In the event of a blackout, the network was completely blacked. There was no exchange of power. Loads were not getting their power supply. Generators were not able to generate power. Even if they were able to generate, the power did not find a path through a transmission line to serve the corresponding load. That is what is meant by blackout. And in a general sense, blackout also means that the entire network was affected. So one of the first reported major blackout which happened was the Northeast blackout in 1965, in which almost 30 million people were affected for close to 13 hours. And the reason why this network was blacked out or the loss of load happened, so many people lost their luxury or the effect of utilization of electricity for so many hours, was because of the fact that one of the major power lines, which was having its own protective relay device, the protective relay device had maloperation, and the maloperation was because of the wrong setting which was given to the relay, as a result of which at 5:15 evening hours, 5:16 p.m., this major power line, which was carrying significant amount of power, specifically given the fact that it was evening hour, where evening hours, as I have mentioned in the duck curve or the load curve, evening hours the network load goes up. So one of these power lines which was heavily loaded, because the network load was very high, because of this misprogrammed setting in the relay, the line got tripped. As a result of which, again, network physics has to be true. So since power is being generated and there are entities which would consume power, the electrical power or current always figures out a way of where it should flow. So when one line got tripped or was out of operation, power now was flowing through other lines, which eventually made these non-noded lines to become to carry power or current which was close to their maximum loadability limit. And the moment a line starts carrying power or current which is close to its maximum loadability limit, line protection systems or schemes or tripping schemes come into picture, because of which the neighboring lines, when they got overloaded, their relays again tripped the lines, and as a result of which there were several lines which became out of operation because of maloperation of one such line, because other lines were getting loaded. So essentially there was generation, there was load, but there was no corridor through which generation can transmit its power to the load. So as a result of which, generators, they also, when they don't find a way to transmit their power, power cannot be created, cannot be destroyed, it can only be transmitted, stored, or passed on. It cannot be created out of blue. So generators, when they are generating power and there is no path for this power to go out, generators started losing their synchronization, and as a result of which, in addition to lines being now tripped, generators also got tripping, and as a result the entire network had a blackout. And with one power line tripping, which led to other lines getting tripped, which led to other generators also getting tripped, it was all a cascaded event. It was a chain reaction. So one simple minor incorrect relay setting led to sequence of events or cascade of events which resulted in the blackout of the entire network. There are several such blackouts which have happened ever since. The links that I have shown here, there are few interesting links in which you will be able to understand what this blackout is in more detail, how things have happened, what are the recent blackouts that have happened. In fact, every now and then some grid in the globe, in the Mother Earth has this situation. Some are minor, some are major. The most recent major blackout which happened was on August 25, 2025, where the country Chile had its entire power network out. Again, reason was that one of the protection systems, it malfunctioned because of electronic switching or incorrect setting, due to which A high voltage transmission line got non-operational. It was supposed to operate, it got non-operational, and as a result of which neighboring lines got loaded and then cascading event happened. So the reason for explaining all this in terms of blackout is that in all these events of blackouts, the network was not operating in a secured fashion. That means in case of outage of a generator or a line, which eventually is what is called as contingency. In fact, contingency as it is refers to a situation or an event which is uncertain, which cannot be predicted that it will happen for sure. It may happen, may not happen, and in daily human life, we always encounter contingencies. We never know precisely what will happen next. So same is the case for the power network also. It is impossible to predict that at the next instant of operation, this particular line will remain operational because of bad weather, because of overloading, or because of n number of reasons. The network faces these uncertain events. In fact, sudden load change, sudden load drop, these are also contingency events. And in order for the network to not go into a blackout mode, certain corrective action or control action needs to be in place so that the network is still able to sustain the impact of these contingencies while ensuring that generation and load balancing is met. That is essentially what is the purpose of contingency or security analysis. It's a very specific tool, but in a generic sense, we will understand what these details are. So, as you would have already gotten a flavor of by now, that security or power system security is basically trying to maintain the normal operation of the power network. What is normal operation? There are mathematical ways of quantifying the same. I'll come to those conditions in a moment. So, security is all about that the network, power network is able to operate in a normal condition even during unforeseen events which we call as contingencies. Usually these contingencies in power network, they are either forced outages of elements or equipments because of maintenance scheduling or because of any uncertain event. The line was supposed to operate but it has now got out. Load change is also categorized as contingency. Unforeseen load change is also part of contingency. So security, as I mentioned in detail, is basically the ability of the network to operate in a reliable condition, not only in the present condition, but also for the next sequence of events that are going to happen where contingencies may happen. By normal condition, there is another inference to normalcy. The other inference is no network related variable, that is no bus voltage, magnitude, no phase angle, no power flow on a line. These are all physical quantities. These limits or these quantities should also be within their physical or operational limits. There are ways of how these limits are determined. They are often determined by the network operator or through the physical experience of how a particular voltage can go down to or can go up to. Transmission lines, their ratings are specified by the manufacturer. Every line has a maximum current carrying capacity. If we expect the line to carry current 10 times beyond its capacity, obviously the line will have heating effect because of I square R loss, and then eventually it will melt and break down. So that's what the physical and operational limits are. Operational limits are defined by the operator, whereas physical limits are defined by the corresponding manufacturer or the way the corresponding element or equipment has been designed. In other words, security is also the ability to maintain normalcy in the power network even during contingencies. And as I mentioned, contingencies are uncertain events. So if we expect that for every probable contingency, the network security should be maintained, then yes, ideally speaking, that should be the case. But often the network cost or operational cost or maintenance cost would go up, because if we start catering to all possible combinations, First of all, those number of combinations would be very, very high. So in order to have a balancing between the investment involved in setting up the system which would control and maintain the network during contingency and the number of contingencies that can occur ideally in the network, in order to have a balancing or a trade-off, based on operators' experience, operators generally plan or do security function for credible contingencies which have higher probability, the probability being more than a particular threshold based on the operator's confidence. The normalcy, as I mentioned, the quantification part, the normalcy is when all real and reactive power loads, they are satisfied by some generator or set of generators. And as I was mentioning about these physical quantities, they are also within their desired physical or operational limits. The letter L essentially refers to the factor that loads are being met, whereas the letter C here essentially means that the constraints, which in a way is another way of stating the limits, the corresponding inequality constraints or equality constraints which ensure that the load is met, the limits are being met. The constraints, mathematical constraints, if they are being met, then we also associate that condition with the letter C. So, as I was mentioning, the physical and operational limits, every line has its flow limit because every conductor has a maximum current carrying capacity. Buses also have their limits from voltage stability or from long-term or short-term operational perspective. Network frequency has limits. If the frequency goes up or the frequency goes down, area control error tends to go up, and then scheduling or control error or desynchronization events, their possibility goes up. Generators have physical limits on how much real and reactive power they can generate, which we also infer as capability curves of synchronous generators. There are limits on how much spinning reserve or hot or cold reserve can be managed or placed at every generating station. Thermal limits, they have their own ramp rate limit. We discussed this briefly when we discussed the economic dispatch. A transformer tap can not change 24 times or 48 times in a day. If it starts doing so, it's a mechanical device. Because of wear and tear, the transformer lifespan would go down, and that is what is meant by limited control action from the perspective of lifespan or maximization of lifespan. So every physical equipment also has limitation of how many times it can be turned on or turned off. Frequent turning off and turning on weakens the stress, increases the stress in the system, because of which mechanical devices can have wear and tear, and that's where this constraint can also be mathematically realized and included in the corresponding normalcy operation. Contingencies, as I mentioned in the previous slide, that these could be forced or unforced generation outage, these could be forced or unforced line or transformer outage. This could also be scheduled or unscheduled load or generation change. Forced outages, they happen generally because of maintenance perspective. Unforced outages, they are uncertain. These could happen because of excessive loading, protective system maloperating, during case of swing events, power swings. So these things can happen. Scheduled changes are not so detrimental changes because operator is probably aware of those changes. Unscheduled changes are those cases where, because of a forced outage of a line or a generator, the corresponding injections have also changed. So with that, let's see what types of power system security exercises exist, what time frames of analysis is possible for power system security. The discussion that I am going to make for power system security classification, similar classification is also true for other modules that we are going to discuss, which will be discussed at length when we discuss the corresponding module. So in context of power flow analysis, I have mentioned specifically that it is a steady state analysis exercise. So if steady state framework of voltages can be obtained at every bus in the power network, then one can also imagine or wonder that probably we can have time varying estimation or dynamic estimation of voltages also, because network is not a stagnant quantity. Its situation doesn't remain stagnant. Load changes, contingencies happen, generation changes, and all that brings into a quasi-static or a dynamic framework. So the same case is also true for system security. The first classification from the steady state perspective is steady state security or static security, in which we don't involve time differential equations, which are not necessary, because we assume that whatever is happening, its impact has subsided and things are now not changing in time. Whatever disturbance or contingency had to happen, it has already happened and its transient effect has gone by. In steady state, we want to see whether the system will be able to handle the impact of the contingency or not. So there are two ways or two broad again classifications of static security. One is from the perspective of line flow limits, which we would call as overload security or line flow security, in which the line ratings or flows are compared with their corresponding maximum power limit or MVA limit. The other form of security is known as voltage security, in which whether the bus voltages are within their respective maximum and minimum limits for the given contingency that has happened. In case the voltages are low, they may degrade the performance of the industrial motors or domestic appliances. In case the voltages are very high, the insulation installed in the conductor or transmission line or transformer, its lifespan may also get impacted. And this may also affect the performance of the lighting and heating loads also. The other form of voltage security, which we will discuss at length when we discuss the voltage stability or instability module, is about what can be the maximum load, specifically real power load, that a network can satisfy or handle, provided the corresponding voltage drop across the lines, because if the load values go up, the corresponding current carrying capacity of lines also has to correspondingly go up. So the capacity doesn't go up, but the currents in the transmission line have to go up in order to feed more power to the load. If current goes up, the voltage drop across the line has to go up. If the voltage drop has to go up, then it is possible that at the source end we have stiff voltage regulating devices, but of the same regulation, the corresponding load and voltage will be very, very low. So there comes a point that if the load keeps on increasing, the load voltage at the receiving end tends to go down, and there comes a situation that after a minor incremental change or increase in the system load, the network will experience voltage collapse. That means no matter what voltage regulation reactive power support devices we bring in, when the load is close to its voltage collapse capacity, the system will face a blackout event or a cascading event. The system will not be able to recover from this voltage collapse point, which is determined in the study of voltage stability. So that's another form of voltage security. So for our current discussion, we will focus the first two bullets at length. The third bullet will be discussed at length when we discuss the voltage stability module. The next broader classification of analysis is dynamic security. If static security can exist, then definitely dynamic security can exist, where I was mentioning that here in this analysis, one tries to understand the time varying effect of how the system states change if the contingencies happen. So dynamic security, I'll just explain that, enumerate that, but we will not be discussing as part of this particular course. Dynamic security is more to do with offline analysis, which checks the static security again in consideration of the steady state limits, while also looking at the time varying stability problems, specifically rotor angle stability limit and the frequency deviation or dynamic voltage stability limits. Again, this aspect will be discussed at length, but not from the perspective of dynamic security. We'll discuss exclusively what rotor angle stability is, what frequency deviation or frequency stability aspects are. So coming to the first process flow based model, which was proposed by Diliaco in 1967. Diliaco presented a process flow diagram in which Diliaco stated that if the system experiences certain changes because of contingencies, then how the system behavior changes. So first of all, one has to understand what is meant by the state. We have already evaluated these states in power flow analysis module. We'll also understand the importance of these states when we discuss at length the state estimation exercise as part of security analysis module. States are essentially defined by all bus voltage phasors. Why these are called states? If we know all bus voltage phasors, then we will be able to find all other quantities, currents, injections, flows, everything for a given known network information. So, since the system is having variation, these states are also not constant, they are also dynamic. And Diliaco stated that under normal condition, which is wherein this model 3 state model comes in, under normal condition, both load and constraints, they are being met. The L and C that I am written here, they are the same L and C which was present on slide number 5. By L and C being green, it should be understood that all loads are being met and all network constraints are being met, and that is where the normal operation comes in. Now, during this normal operation, if a contingency happens, which could be outage of a line, generator or load change, then the system operation goes into an emergency mode where loads are still being met, but one of the constraints or more than one constraints are at their maximum or minimum limits, or in fact certain constraints have even violated their limits, certain variables have even violated their limits. So, if then nothing is done, if the system operation continues to be in emergency mode and nothing else is done, then as I was mentioning the discussion on blackouts, if nothing is done, since constraints are being violated, it will lead to more violations, and as a result of which it can have a blackout or partial blackout. Once system has gone into a blackout phase, then the network operator has to restore system operation where restorative action or restorative mode comes in. In restorative mode, the network is restored so that no system constraint is ever violated. There can be loss of load, that is not an important part, and that is where L is in red. The restorative mode ensures that first the system has to be ready and then only the system load can be brought up. It's impossible to sort of have restorative mode where right after restoration all loads are restored. We often experience blackouts, at least in India, in rural or semi-urban rural places, where because of bad weather, the network operator or the corresponding DISCOM or utility turns off the network so that during bad weather, extreme storm or rain, the lines don't get perturbed, branches if they fall, it creates more chaos. After the weather bad event has gone by, then the network utility or DISCOM starts energizing the network and gradually it is done. It's not that the entire city of Kanpur would get electrified in a single switch go. The electrification or restoration happens in phases, which is where constraints are important that they should be satisfied. Load is not so important. And after all the restorative actions are done, the system would move from restorative mode to normal mode where the red L becomes green L. In between, if emergency mode is being encountered and the system has to be prevented to not go into a blackout mode, then the operator also can bring in emergency corrective action wherein because of high chances of constraints being unsatisfied, if the loads can also be curtailed. So, one of the options of emergency corrective action is load shedding. That if the system is not able to meet the corresponding load demand because of which one line flow is trying to get overloaded or one line is trying to get overloaded, let us bring down the load so that the constraints can also being not being in red can go back to the green color zone where constraint can be met. So, load shedding is one possible way of emergency corrective action, and that is where if you see the black lines are natural actions. That means if nothing is done, that's how the sequence of events would happen. In order to prevent the system not go into emergency or restorative mode, there comes the control action, wherein the emergency corrective and restorative actions come in. Now, this three-phase model or three-state model is good. The only problem was in 1978, Fink and Council, they modified this three-state model to explicitly bring in the blackout state, which is called as in extremis state, and also bring in another intermediate state known as the alert state. There is a reason why these two were brought out. So, let me explain those one by one. The normal condition is that all loads and constraints are being met. If a contingency happens, it's not necessary that every contingency is a critical contingency. Certain contingencies are detrimental, certain contingencies are not detrimental. If a contingency occurs and it happens to be a non-detrimental contingency, then still in that situation also load and constraint can be met. And in order to prevent the system from alert mode to normal mode, the operator will make use of the preventive action. If preventive action is not sort of encountered or controlled, then there can be a cascading effect where from alert mode the system goes into an emergency mode. Even if when the system is in emergency mode, there is still a control action possible, which is often called as the corrective control action plan. I'll explain preventive and corrective in detail when I go to the next slide. Suppose nothing is done, no preventive action happens, no corrective action happens, then from emergency mode, it can again, it will go to a blackout condition, and in blackout, entire network is blacked out. So, from there, either you bring in corresponding corrective action or emergency corrective action, which brings in the restorative mode, and from restorative mode, further actions need to be taken in, that is, loads are restored so that the system goes back to the normal mode. So, each of these terms, preventive, restorative, corrective, they have their significances, which is explained in the corresponding discussion here. So, on top of Diliaco model, Fink and Carlson brought in two additional states. They are alert and in extremis state to explicitly define the control actions that the operator takes. Preventive, as the term says, preventive actions are those which essentially are applied or implemented or prepared for infeasible cases. Infeasible from mathematics essentially means that the constraints or physical and operational constraints cannot be met. In optimization framework, that's what infeasibility means. So, suppose a contingency happens which leads to essential violation of one of the physical constraints or operational constraints, then that contingency is called as an infeasible contingency or a detrimental contingency. Now, preventive mode, why it is so useful or used for infeasible cases? The reason is like this. If the network operation is at the current state and an infeasible contingency happens, if the infeasible contingency happens, then essentially the system would immediately go from normal to emergency mode. It will go through the alert mode, but then the alert mode is not so evident because it's a very critical detrimental contingency. Once the system has gone from normal mode to emergency mode, from emergency mode, there are either two possibilities, either bring in corrective action or semi-emergency corrective action, which is essentially a costlier plan. So, preventive mode tries to prevent the system before the contingency has actually happened, so that least cost mode of operation is still maintained, economics is still maintained as it is costly and slow, because a priori knowing what generation change and voltage support would be required so that they can be activated is what makes the preventive mode come into practice. You may also question, sir, that in infeasible case of contingencies, why can't we have corrective action? Corrective action are meant for those situations where the system operation is not at stake. The system has not gone into a blackout or into an emergency action. So, the corrective actions, they are not always regularly favored. So, basically for feasible contingencies, one suggests that corrective actions should be brought into place. because these are not significant contingencies. So, as and when required, the operator can change the system operation or change the settings so that these feasible contingencies can be catered. And those measures are what are known as load shedding method or intentional tweaking of the voltage at the receiving end, which is also known as brownouts. By reduction of voltage, if there is a voltage dependent load, then the load at the receiving end also would go down, which would eventually bring down the load consumption. So, in terms of security function at energy management systems or EMS systems, there are three phases. The first phase is security monitoring, which is essentially done by state estimation. State estimation helps us in providing these system states from the possible measurements obtained from SCADA, RTUs, remote terminal units, or phasor measurement units. One can also wonder that why power flow analysis is not used or done as part of security monitoring, because power flow also provides similar states. Please have patience. The next to next discussion, it will become evident why state estimation needs to be learned and how it is different from power flow analysis, whereas both of these provide these system states, which are bus voltage phasors. Then comes the contingency analysis or security analysis based on the obtained states, which define or fit to the system operation to one of these models that are shown here. Then comes the situation of contingency analysis, which filters out which credible contingencies are detrimental or non-detrimental. Detrimental are the infeasible contingencies and non-detrimental are the feasible contingencies. By using appropriate tools, techniques, credible contingencies, detrimental credible contingencies are then categorized further into critical and non-critical contingencies. And that is where our main focus of discussion would be in this module. The last phase is optimization or security enhancement, where different corrective control actions are planned for critical contingencies, either they are feasible or infeasible. So, usually we prepare preventive plans, as I mentioned, for critical infeasible contingencies, whereas corrective plans are prepared for critical feasible contingencies. The reason, as I would mention again, why preventive plans are important for critical infeasible contingencies is once the system has encountered an infeasibility, it is as good as close to being in a blackout condition. So, for infeasible cases, things have to be planned a priori, and in order to have this plan, an operator has to know that actually this contingency is a critical infeasible contingency. The operator cannot have the luxury to wait and watch, okay, let me see how the contingency is happening. If everything goes well, then my operation would be at stake. If everything goes well, then there is no need for security analysis or security enhancement. If the contingency is happening and then infeasibility occurs, loads are not met, cascading happens, brownout happens, blackouts happen, then the operator cannot save the system at all from blackout. So, can something be done is where the preventive actions come, where day ahead or pre-planned or in anticipation of the event to occur, the system operator plans corresponding generation, reserve, voltage support devices, so that in case these events occur, then the system will still be saved. And hence it is a pre-planned action, which is what makes it costlier. Corrective plans are those which are not so costly and they would be implemented because when the feasible contingencies occur, because the constraints can still be handled. So, this process flow diagram essentially shows what security monitoring, assessment and enhancement is. Our primary focus, the next discussion onwards, would be on the assessment. The third and fourth discussions of this particular module will briefly talk about what security monitoring or what essentially state estimation is and what is meant by enhancement. So, if I were to just understand or explain what this security function exercise is, it is a cyclic exercise. That means it keeps on running, or the corresponding algorithms keep on running, they never stop running. So, given a power network in the present operating condition, states are obtained from state estimation. Based on these states, a preliminary threat analysis is done, which either sort of detects the threats. If they don't detect the threat, that means everything is okay. So, system goes back to the new condition and this repeats. If threats has detected, then contingency analysis categorizes these threats into critical or non-critical contingencies. If these are non-critical, absolutely no problem, system control action can still be handled. If these are critical, then whether these are feasible or infeasible cases. If these are infeasible cases, then preventive OPF has to be done from enhancement. If these are feasible cases, then corrective OPF has to be done. And these action plans are saved and prepared and stored, and based on the occurrence or sort of actual happening of these contingencies, these plans are implemented as and when needed. And then again the system goes back to its new operating condition, and this cyclic process continues, it never stops running. That's where I would end or conclude my discussion. The next discussion would be on details on contingency analysis or the phases of security analysis. The last this slide, we talked about phases of security function. In the next discussion, we will talk about different phases which are involved in security analysis. With that, I conclude the discussion. Look forward to more discussion. Thank you.